In the realm of online learning, providing timely and accurate feedback to learners is paramount, particularly in skill-based learning, where learners must grasp the underlying concepts and mechanisms of a skill to apply it effectively. However, videos, a common tool in online learning, cannot assess or comprehend the skills being taught. Meanwhile, generative AI methods, although effective in searching and retrieving answers from a text corpus, lack true understanding, limiting their ability to provide explanations of skills or assist with problem-solving. This paper proposes a novel approach that integrates cognitive AI and generative AI to address these challenges. By employing a structured knowledge representation, the task method knowledge (TMK) model, the authors encode skills taught in an online knowledge-based AI course. Leveraging techniques such as large language models, chain of thought, and iterative refinement, the authors outline a framework for generating reasoned explanations in response to learners' questions about skills. The paper begins by highlighting the significance of online education, particularly in the context of adult learners who require reskilling and upskilling. The authors note that simply watching educational videos and answering quizzes fosters passive learning, whereas active forms of learning, such as those that involve reasoning and problem-solving, lead to deeper understanding and increased cognitive engagement. The authors argue that there is a scarcity of literature that considers how educational technology can capture a deep understanding of the skills being taught and address complex or novel learner inquiries. They propose that by integrating cognitive AI and generative AI, it is possible to create a system that not only represents skills but also provides explanations and answers to learners' questions. The paper highlights the limitations of generative AI methods, such as large language models, which, despite their remarkable capabilities, do not autonomously manifest any understanding of their assigned tasks. The authors propose a novel theory and application of learning that emphasizes a hierarchical representation of skills, where understanding a skill involves understanding its components, their interactions, and the teleological aspect. The authors identify the need for a system that can provide reasoned explanations and answers to learners' questions about skills, and propose a framework that integrates cognitive AI and generative AI to achieve this goal. The paper outlines the theoretical foundations of the proposed approach and highlights the significance of integrating cognitive AI and generative AI to enhance the representation and explanation of skills within online learning environments. Equations, algorithms, and mathematical concepts are not explicitly presented in this section, but the authors mention the use of techniques such as chain of thought and iterative refinement, which will be discussed in subsequent sections. Figures, tables, and graphs are not included in this section, but the authors provide a clear and concise overview of the research question, methodology, and significance of the study. The authors assume that the proposed approach will be effective in enhancing the representation and explanation of skills within online learning environments. However, they acknowledge the need for further research to validate the effectiveness of the proposed approach. The limitations of the study are not explicitly stated, but the authors highlight the need for further research to address the challenges of skill-based learning in online education. Overall, this paper proposes a novel approach that integrates cognitive AI and generative AI to enhance the representation and explanation of skills within online learning environments. The authors provide a clear and concise overview of the research question, methodology, and significance of the study, and highlight the need for further research to validate the effectiveness of the proposed approach. This research explores the development of an intelligent agent, IA, capable of generating contextually rich and reasoned explanations for learners' inquiries about skills, leveraging the convergence of cognitive AI and generative AI. The authors employ a structured knowledge representation framework called TMK, task method knowledge, to conceptually capture problem-solving skills, decomposing them into three components: task, method, and knowledge. They propose two research questions, RQs, and research hypotheses, RHs, to explore this convergence. RQ1 investigates how an IA can explain how a skill works and the results of the skill in a specific instance, with RH1 suggesting that this can be achieved by inspecting the design and simulating the execution of the skill, reflecting on the trace of the simulation on the instance. RQ2 explores how an IA can inspect the design of a skill and reflect on the trace of simulating the skill on an instance, with RH2 proposing that this can be accomplished by representing the skills design as a TMK model and keeping a derivational trace of actual processing on the instance. The authors discuss related work revolving around two themes: representing skills in AI and generating answers or explanations using AI. Prior work has focused on representing cognitive skills using rule-based formulations, ontology-based frameworks, and knowledge-based approaches. In robotics, skill representation is a foundational problem for applications like planning, task completion, and human-robot interaction. Studies have also investigated knowledge-based question answering, KBQA, using various AI techniques, including hierarchical knowledge representation, automated logical theorem provers, and hybrid NLP-based architectures. The authors highlight the potential of leveraging cognitive AI and generative AI methods for various use cases, but note that few studies have modeled problem-solving skills as abstract devices that can be introspected for generating explanations to user questions within online learning environments. To address this gap, the authors propose a novel method that models a skill taught in an online course using a structured knowledge representation, leveraging generative AI methods to generate reasoned explanations in response to users' questions about a skill. In cognitive science, declarative memory is categorized into semantic and episodic knowledge. The proposed interactive video system, Ivy, draws inspiration from this theory to answer user questions. Upon receiving a query, Ivy classifies it as either related to semantic or episodic knowledge using a large language model, LLM, based on GPT 3.5 Turbo, which performs zero-shot classification with in-context examples. Semantic knowledge questions, typically formatted as, "What is X?" or "Explain X," are the focus of this paper. The task method knowledge, TMK, model is central to Ivy's functionality, guiding both retrieval and response generation. To integrate a new skill or concept, Ivy follows a three-step process: task definition, method specification, and knowledge representation. Task definition involves identifying the goal, allowable inputs, and expected outputs of a skill. Method specification describes the mechanisms for accomplishing tasks using a deterministic finite-state machine called an organizer. Knowledge representation defines objects, concepts, and relationships, including object properties and logical expressions. Once categorized as semantic knowledge, questions are further classified based on the TMK model components. Ivy distinguishes whether a question relates to the knowledge model, the method, task model, or the multi-model. If irrelevant, it is classified as such. The LLM performs zero-shot classification, providing descriptions and examples of each category. Knowledge model questions focus on object properties and logical connections, while method, task model questions concern task mechanisms and steps. For instance, in a sorting algorithm, a knowledge model question might ask about number properties, whereas a method, task model question might inquire about the sorting process. Ivy's question classification system categorizes queries into three distinct types: knowledge model, method, task model, and multi-model. Knowledge model questions focus on conceptual states, transitions, and actions that guide the system, without executing the task. Method, task model questions delve into the mechanisms for task completion, while multi-model questions explore the interplay between objects, concepts, and relationships within the environment and task mechanisms. Once classified, Ivy retrieves the most relevant documents from the TMK knowledge base through a two-step process: K-score calculation and document retrieval. The K-score calculation determines the level of detail and complexity in the response, ranging from brief responses to comprehensive responses spanning multiple paragraphs. The document retrieval process, facilitated by the FAISS library, retrieves the top K relevant documents based on the input question, ranking them according to their relevance. For knowledge model questions, only the top K knowledge documents are retrieved, while for multi-model questions, the top K documents from a combined set of knowledge, task, and method documents are retrieved. For method, task model questions, the retrieval focuses on the most relevant task document and its associated method document. Ivy's response generation process involves iterative refinement for questions classified as knowledge model or multi-model. This process generates an initial response based on the top most relevant document and then refines it by incorporating additional information and context from the remaining K1 relevant documents. Each step in the iterative refinement process involves a call to the LLM to generate natural language responses. Figure 5 illustrates the iterative refinement flow in Ivy, a system leveraging large language models, LLMs, for answering complex questions. The process begins with initial response generation, where the LLM takes the user query, expected verbosity level determined by the K-score, and the top relevant document as context. A refinement step follows, synthesizing information from remaining relevant documents to refine the initial response and generate a more comprehensive answer. For method, task model questions, Ivy employs a chain-of-thought generation process. This involves transition extraction, where relevant transitions are extracted from the topmost method document, and transition explanation generation, where these transitions are used to generate a natural language response explaining the task completion process. Chain-of-thought prompting guides the generation process, with multiple in-prompt examples provided to the LLM to demonstrate required reasoning and context. A worked example using the classic river crossing problem illustrates this approach. In this scenario, 3 missionaries and 3 cannibals must cross a river using a boat that can carry at most 2 people, without violating the rule that the number of prisoners on either side of the river must not exceed the number of guards. When a user poses the question, "Who is a guard?" the system creates a simplified task management knowledge (TMK) model for the river crossing problem. This model includes steps such as moving the boat to the opposite bank, loading the boat with selected individuals, unloading the boat, and checking for constraint violation. The knowledge representation includes concepts of guards, prisoners, boat, relationships between them, and rules governing individual movement. The question is classified as a knowledge model, method, task model, multi-model, or irrelevant question using a query to the LLM that includes a description of the TMK model components and a prompt for classification. This classification determines the subsequent steps in the iterative refinement flow, ensuring accurate and comprehensive responses to complex questions. The task method knowledge, TMK, model is employed to structure the knowledge base and generate responses to user queries. This model comprises 3 components: task, method, and knowledge entities, including guards, prisoners, and other relevant entities. When classifying a question as a knowledge model question, the system calculates a K-score to determine the verbosity of the response. For instance, a K-score of 2 indicates a short answer. Using the FAISS library, the system performs a similarity search between the user query and all knowledge documents in the TMK knowledge base. The top 2 documents with the highest similarity scores are retrieved for response generation. These documents contain information about the definition and description of guards and their relationships with prisoners. The system employs an iterative refinement process to generate a response, initially using the top most relevant document to generate an initial response. This response is then refined by incorporating additional information from the second document. The large language model, LLM, synthesizes the information from both documents to generate a comprehensive answer. The TMK model effectively structures the knowledge base and responds to user queries by capturing the hierarchical structure of skills, enabling the generation of reasoned explanations. This approach has potential applications in online education, where dynamic and interactive content is essential for effective learning. Furthermore, the system's focus on semantic knowledge question answering can be expanded to episodic knowledge question answering using the organizer components in the method specification of a TMK model. The proposed TMK-BASED system is evaluated using a set of metrics that assess its performance in generating responses that cover relevant information, provide accurate and relevant details, and maintain uniformity across multiple runs. The completeness metric evaluates the amount of relevant information covered in the response, with a 5-point scale ranging from very incomplete to very complete. The precision metric assesses the accuracy and relevance of the information provided, with a 5-point scale ranging from very low precision to very high precision. The consistency metric examines the uniformity of responses for the same query across multiple runs, with a 5-point scale ranging from very inconsistent to very consistent. To ensure robust evaluation, the authors plan to implement a mixed methods approach that combines automated metrics, such as Blue and Rouge, with human evaluations to measure output quality more effectively. This approach acknowledges the need for further refinement and validation of the proposed metrics. Future work includes refining the evaluation mechanism, automating the creation of TMK models, and enhancing generative AI techniques. The authors acknowledge the contributions of several individuals and organizations, including the National AI Institute for Adult Learning and Online Education, which supported this research through NSF grants. The proposed evaluation metrics and mixed methods approach aim to provide a comprehensive assessment of the TMK-BASED system's performance, highlighting areas for improvement and informing future research directions. I'm ready to refine the transcript. However, I don't see the original content provided. Please share the transcript you'd like me to refine, and I'll transform it into a direct, concise, and technically accurate summary suitable for voiceover narration. However, I don't see the original content that needs refinement. Please provide the transcript of the explainer video summarizing the research paper, and I'll be happy to refine it according to the guidelines you provided.